So, you're looking at a complex molecule and wondering, how on earth do chemists map out exactly what is connected to what? Well, you are in the right place. Today, we're diving into one of the most revolutionary tools in organic chemistry, distortionless enhancement by polarization transfer. Yeah, it's a bit of a mouthful, so we just call it DEPT. Make no mistake, DEPT is an absolute game changer in nuclear magnetic resonance, or NMR, spectroscopy. It's basically the ultimate technique for determining the exact number of protons attached to a carbon atom.
Picture this, you're a molecular detective. You're trying to deduce the exact structure of this unknown microscopic molecule. Now, you know the carbon atoms make up the scaffolding, right? But to truly nail down the structure, you have to figure out exactly how many completely invisible hydrogen atoms are attached to each specific carbon. It's kind of like trying to count the passengers inside a car that has totally tinted windows. So how do you count what you can't even see?
Okay, let's dive into this. Here is our roadmap. We'll kick things off with the molecular mystery of NMR, unpack the decoupling dilemma, introduce our hero, DEPT Spectroscopy, crack the carbon code, and then we'll actually solve some real chemical structures.
All right, starting with part 1, the molecular mystery.
To really get what our molecular detectives are doing, we have to look at the fundamental magic of NMR. You see, certain atomic nuclei behave as if they're spinning. Any nucleus with an odd mass or an odd atomic number, like hydrogen-1 or carbon-13, has this quantized spin angular momentum. It basically turns them into tiny little magnets. When we apply a strong external magnetic field, which are those big arrows you see there, these tiny nuclear magnets are forced to make a choice. They either align with the magnetic field in a lower energy state, or they oppose it in a higher energy state. And honestly, that behavior is the entire foundation of how we detect them.
Now, standard carbon-13 NMR is brilliant at telling us the number of distinct, non-equivalent carbon atoms in a molecule. If you have 5 unique carbon environments, boom, you get 5 distinct peaks. But there's a catch. To make those peaks crisp and easy to read, we use a process called proton decoupling. It cleans up the spectrum beautifully, but it hides a critical secret. We completely lose the vital information about how many hydrogen atoms are actually attached to those carbons. Basically, we just tinted the windows on our molecular cars.
Which brings us right to part 2, the decoupling dilemma.
Historically, chemists were stuck with a super frustrating trade-off. On the left side, we've got standard broadband decoupling. Beautiful, clean, single peaks. It even boosts your signal-to-noise ratio because of something called the nuclear Overhauser effect. But again, zero information about attached hydrogens. Then on the right, we have this older compromise called off-resonance decoupling. It actually retains the one-bond couplings between a carbon and its attached hydrogens, letting you use the n+1 rule to count them. But as you're about to see, this comes at a pretty steep visual cost.
I mean, just look at this off-resonance decoupled spectrum of 1-propanol. 1-propanol is a relatively simple molecule, and you can already see the signals splitting into quartets and triplets. The peaks are spreading out everywhere. Now imagine trying to use this old-fashioned technique on some massive, complex drug molecule with 30 carbon atoms. The spectrum just becomes this tangled, overlapping forest of messy multiplets. It is incredibly frustrating to resolve.
Fortunately, we don't have to deal with that anymore. Let's hit section 3. Enter DEPT Spectroscopy. Enter DEPT. This technique is basically our highly sophisticated sorting machine. It completely solves that decoupling dilemma we just talked about. By using a modern Fourier transform pulsed spectrometer and some clever computing, it gives us the exact same hydrogen counting information as off-resonance decoupling, but it does it far more reliably and with crystal clear presentation. It literally takes all the guesswork out of the equation.
So how does this magic actually work? Think of the DEPT process as a really complex, highly choreographed dance. First, the sample gets hit with a precise sequence of pulses and delay times in both the hydrogen-1 and carbon-13 channels. And here's the genius part. By strategically altering the duration of these pulses, the carbon atoms start to exhibit different signal phases based entirely on their hydrogen passengers. A carbon carrying 3 hydrogens will literally behave differently in the machine than a carbon carrying 2, or 1, or none at all.
Let's see exactly how we read these signals in section 4, cracking the carbon code.
So the crucial point here is knowing how to read the different DEP experiments. You can think of this table as your decoder ring. The spectrometer plots different subspectra based on those pulse durations we mentioned. In a DEP45 experiment, any carbon with at least 1 hydrogen gives a positive peak. Quaternary carbons, the ones with 0 attached hydrogens, they just stay completely silent, no peak at all. In a DEP90, the delay is tweaked so that only methane carbons, carbons with exactly 1 hydrogen, show up.
But the absolute workhorse, the most powerful trace, is the DEP 135. Look at that rightmost column. Methane and methyl groups show up as positive peaks, but methylene groups, carbons with 2 hydrogens, actually invert. They show up as negative peaks.
Let's really cement those key rules for the DEPT 135 spectrum, because this is exactly what you'll be looking at in the lab. Rule 1, carbons with odd numbers of hydrogens, your CH and CH3 groups, point up, positive peaks. Rule 2, carbons with even numbers of hydrogens, specifically your CH2 methylene groups, point down, negative, inverted peaks. And rule 3, quaternary carbons with no hydrogens vanish completely. By just comparing this trace to a standard decoupled spectrum, you can instantly, definitively categorize every single carbon atom.
Okay, let's put our decoder ring to the test. Section 5, Solving Real Structures.
Now, what's really interesting about this slide is how cleanly the data is presented. We're looking at the deep spectra for isopentyl acetate. That bottom trace, that's our standard broadband decoupled spectrum, showing all 6 carbon environments. Now put your detective hat on. Look at the peak on the far left of that bottom trace at 172 parts per million. That is carbon number 6, the carbonyl carbon. Notice how it completely disappears in the deep 45, 90, and 135 traces right above it? Bam! That instantly confirms it has 0 attached hydrogens. Next, look at the very top trace, the deep 135. Do you see those 2 peaks pointing downwards at 37 and 53 ppm? Those are our inverse peaks. That immediately tells us that carbons 3 and 4 are methylene, or CH2 groups, and the peak at 53 ppm is shifted further downfield simply because it's deshielded by that nearby electronegative oxygen atom.
That downward-pointing peak, that is literally the smoking gun of the deep 13.5 subspectrum. Through pure mathematical manipulation of the pulse sequence, the physical properties of these tiny nuclei are translated into a simple visual binary, up or down. It totally eliminates that overlapping mess of off-resonance decoupling and gives us absolute certainty when we're trying to spot methylene groups.
Let's level up and look at a slightly more complex molecule, citronello. Sometimes modern software can process the raw depth data and fully separate it into an edited stack, like you're seeing right here. Instead of just having positive and negative peaks all on one line, the computer literally gives you separate clean traces for CH3 carbons, CH2 carbons, and CH carbons. It's almost like dumping a mixed bowl of fruit into a machine that perfectly sorts the apples, oranges, and bananas onto their own separate shelves. The guesswork is completely gone.
Let's actually decipher a few specific clues from this citronello data. In the standard spectrum, we see 2 peaks in the double bond region, at 124.6 and 131.0 ppm. So which is which? Well, if we check the DP data, the 124.6 ppm peak shows up clearly in the methene CH region. It's got 1 hydrogen. But the 131.0 ppm peak? It vanishes entirely from the protonated traces. That confirms it's carbon 7, our quaternary carbon with no attached hydrogens. Oh, and check out the peak at 60.8 ppm. It's sitting squarely in the methylene CH2 trace. Because it's shifted relatively far downfield, we can confidently assign it to the CH2 group sitting right next to the molecule's electronegative oxygen atom. Literally, piece by piece, DP is letting us build the structure.
And this brilliantly illustrates why DEPT isn't just a cool trick. It's a foundational stepping stone. Once you know exactly which carbons are CH, CH2, and CH3, you can feed that precise data into incredibly advanced two-dimensional NMR techniques. Things like headcore, which stands for heteronuclear correlation. Headcore will actually take your depth data on one axis and proton data on another, and map the exact connections. It shows you precisely which hydrogen is attached to which carbon. Modern organic chemistry completely relies on this exact sequence of discovery.
DEPT spectroscopy fundamentally transformed our ability to see the invisible. It took messy, overlapping data and turned it into definitive, actionable answers. It's the tool that empowers chemists to map out incredibly complex natural products and discover revolutionary pharmaceuticals. So next time you hold a life-saving medication in your hand, ask yourself, how many invisible molecular mysteries had to be solved in a magnetic field just to build it? Thanks so much for hanging out with me for this explainer, and keep exploring.